In the last video, we ended with this form right here for the nilpotent bivector field. So this was the form that we ended on. Now, we're going to rewrite this. So I'm going to take this and just rewrite it. So last video ended with this. So with f being equal to that. But we're going to rewrite this again. So I'm going to first recall that the electric field times, or the negative of the electric field times the relative direction of propagation, kappa, is these anti-commute, so you can rewrite this as kappa here, then E. This is equal to BI. So this is BI. Recall that. So we can write F is equal to E plus BI. Then we can have this right here. But traditionally, what is written actually is this minus plus, and then you switch the positions of this. So you introduce a minus sign up here, which is canceled out by the minus sign that you introduce here. So, but the reason this is done is to encode for handedness, and I'll talk about this a little bit more in some notes on this. So there are some important things to take note here. So I'll say notes. The first is that F was equal to E plus BI. Then F is the canonical bivector. And in the last video, we showed that it was equal to WSK naught, where this S is a relative space-like vector, so it squares to a negative number. This is just the magnitude of K. So you have that K equals this. So this K naught here has no magnitude. It's just a nilpotent vector with no magnitude. And we had that here. Where did we have it? We had it. Oh, I had it actually omega over C. My bad. I forgot. So the paper works in the paper set C equal to the paper set C equal to 1, but I was putting C back in there. So there's that. And we know that K naught is equal to, when you break it into a relative frame, so you do a space-time split, you get 1 minus kappa here, and it's equal to 1 plus kappa gamma naught here, which implies that F is equal to omega S and then times 1 plus kappa gamma naught, which is equal to omega S plus omega S with this parentheses here, omega S kappa gamma naught. And because we can set like terms equal, so we have the E plus BI, and we know that this, or this term right here, because of the extra vector, this must be a bivector and this must be a vector field, but relative bivector, relative vector field. So we're going to get that E, so this implies E is equal to omega S gamma, gamma naught. This gamma naught here goes down here. So this is what we get E as right here. And so that means that we can interpret, you can say, therefore, S is a space-like vector containing the orientation of E and the magnitude, or here, I forgot this factor of 1 over C again. So there should be 1 over C, 1 over C, over C, here. So this has the magnitude C E over omega. So that is what you can think of S as in the decomposition of the canonical bivector. It's the space-like vector containing the orientation of the electric field, so essentially the polarization of the field and the magnitude of the field. Now, the other notes, the minus I in the above equation, so in the above equation, and by above equation I mean here. So when this is minus, so this negative I gives the right-handed circular polarization. So this gives right-handed circular polarization of light, which if you were to visualize it like this, so you have one axis, second axis, and then you have your propagation direction. Propagation direction, go for that. You'll have the electric field will go like this. So you have in the electric field, you end up with, here, I'm just going to, how do I modify the properties again of this? I don't know. We'll see. I'll just do this. So you have a vector going up to it. Oh, wait, well, I should be. So it's kind of hard to tell, but it's kind of hard to draw it too. I'm not the best artist, but this is rotating around, so it's corkscrewing. So it's basically just corkscrewing around this axis. It's going like that, and it's going right-handed, so it's turning this way. If your thumb goes in the direction of propagation, then the field is turning in the direction of the curl of your fingers. So that's right-handed polarization. And then the positive I gives left-handed circular polarization. And left-handed polarization is exactly the opposite. It's if you put your left hand in and you had your left thumb in the direction of propagation, then it'd be turning the opposite way. So that is what left-handed polarization is. So such handedness, so having a right-handed and left-handed polarization, such handedness is called helicity, like a helix, and is a demonstration of the spin one nature of the electromagnetic field. So right away you can tell from the geometry of spacetime that the electromagnetic field is a spin one field because it behaves like with this helicity. And this solution, the above solution, which is a solution to the partial of f equals 0, this solution to the equation in vacuum, Maxwell's equation in vacuum, is called the monochromatic, and it's called monochromatic because, so monochromatic means that you have a constant value, and you only have one. So this right here is the monochromatic solution. So you have one plane wave of light, and it is only one color, omega. Of course, if you break into different reference frames, it looks different, but you only have one. So in one reference frame, you only have one color per reference frame. Okay, so let's now turn to discussing polychromatic. So polychromatic, there's a fly buzzing around, it's bugging me. Polychromatic, also called wave packet solutions. So polychromatic solutions and wave packet solutions basically just means that there are now multiple omegas. They vary, so there are multiple colors of light. And why they can be called a wave packet is because you end up with an integral, so you're summing over, so you have a lot of them. So it would look like you have, like, if this were your intensity, I'll just say intensity, and this right here is omega, it looks like there's a little wave packet. And so that's why when you have multiple colors, it looks like this, and so it's called a wave packet solution. Go over here. So in general, I'm not going to go I'm going to go much more hand wavy, not hand wavy is correct, but I'm not going to be as completely rigorous with the math. I'm going to present it very in an intuitive presentation of the physics because uh, this is a relatively advanced topic. Sorry, I'm trying to get rid of this fly. It's a relatively advanced topic, something that's not covered in a lot of undergrad stuff. I didn't see it until graduate physics, but it was mentioned in undergrad, so it's a relatively advanced topic. So, in general, this equation with the plane wave solution is satisfied, or I'll say by any omega. So it doesn't matter what the actual value of this omega is here. It will always be a solution in this if it's in this form. So it's satisfied by any omega. So if it's satisfied by any omega, then you could say then it is satisfied by the superposition and superposition here just basically means the sum of all solutions. So that means that you can vary omega and then sum all the different omegas together, and because each individual omega satisfies this equation, then their sum does as well. So what this would look like is you'd have the field F sum from negative infinity to positive infinity of, you're going over omega, so you're summing over omega. You're going to have S and K out here. They don't depend upon omega, so you can have them outside of the integral. So you just end up with d omega and then alpha plus omega e to the minus k dot x I, where this k dot x is just this. This comes from k dot x. But this is the relative form. So plus alpha minus of omega e to the k dot x I. So here you end up with all the possible right-handed circular polarization and all the left-handed circular polarization. So right-handed helicity, left-handed helicity. And then you basically sum together all of the different possibilities that there can be over omega, and that because each individual one satisfies this equation, then their sum, which is what the integral does, it sums over them, their sum of f will also satisfy this equation. So there are some important things to note here. Note here that in this thing that alpha plus minus of omega is equal to alpha plus minus the magnitude of omega. Note that these coefficients absorb the magnitude of the field. So the magnitude of the field, so it's magnitude of S. And then you can say such that S squared equals -1. So it becomes a unit vector just giving the polarization direction. And why is absorbing S absorbing the magnitude of the field? Well, it's because of this observation up here, that S contains the magnitude of the field and the orientation. So if alpha absorbs the magnitude, then S only has the orientation. And so that's what this is doing right here. Also, in general, if you know what the Jones vector of polarization is, so basically you can represent polarization in a basis of different types of polarization, then these alphas will give the basis for Jones vectors in the basis of circular polarization. We won't be dealing with that, so I won't cover it, but they can do that. So if you already know what that is, then it's an interesting thing to know. So we can go further. We can consider breaking into a relative frame and adding, and then consider adding all the plane waves going in every possible wave vector direction. So before we were considering changes in omega, but now you go into a relative frame and you sum over all the possible k vectors. So all the possible directions, because remember k vector is the wave vector, so it's the direction of propagation, and it also encodes the um, angular frequency. So now when you sum over the wave vector, you're summing over all the angular frequencies and possible directions. So it's a more general thing. So what this does, what you can think of this as doing, is you break k into its relative frame, where you have the magnitude of k, which this right here, this is just omega, then minus k. So that's what that is. And so that means that s k naught, which is, if you remember, it's k naught is the just pure direction of k, so it's k without the magnitude, so it's just a direction. K naught, and then these coefficients here. So these all become different things. So this becomes something different, this becomes something different. And what they become is s becomes a function of the relative direction. So does k naught. And all this might look like it's much different, but in reality, what we're just saying is that when we break into relative frames, then all of these values will break into relative frames that depend upon these wave vectors. So it's just an acknowledgement that when we break into a frame, this S, when it breaks into a frame, will depend on this K. So we just choose a reference frame to define everything else in terms of. So this then implies that you can write a general plane wave solution, but this isn't necessarily nilpotent, but it is a solution. So this F it's a triple integral because you're going over space. You're going over the relative the wave vectors, so 3 space. Holy crap, this fly is still here. It's really bugging me. So you're going from all possible directions, and you have S, which depends upon K. You have the direction K naught, which depends upon K. And then you end up with alpha plus, which depends upon K. And then you have e to the minus k dot x I plus alpha minus k e to the plus k dot x I. So there's some interesting things happening here. And I'll write them down. So here, the coefficients alpha plus minus of k, these coefficients encode the magnitude and spectral decomposition of the electromagnetic field. So what that means is that this is still a unit vector. This is still just a pure direction. So all of the magnitudes of the fields are included in these right here. So the magnitude of each field is here. And what it means by its spectral decomposition is for each magnitude, how many, or like what the frequency of that particular magnitude would be. So how it decomposes into its spectrum of color. That's what this is. And then the unit vectors S of k encode the polarizations for each traveling mode of the wave of the, I'll just say this, traveling mode. And then in quantum field theory, in QFT, the alpha plus minus coefficients become the creation and annihilation operators for, or specifically the field operators for specific modes of excitation in second quantization. So this is an equation you do see in quantum mechanics as well, except that the physical interpretation changes slightly. Instead of these encoding for just magnitude and color, they actually encode for, rather than magnitude, it's the energy of the excitation of that particle. And then it would be, what do you call it? You'd have, what do you call it? You'd have this would create particles, and this would get rid of, or this would create energy, and this would remove energy. It's a bosonic field, not a spinor field. And then what this says is just that these are just unit vectors encoding the polarization for each k, each wave that is associated to a vector k, this encodes for the polarization. Okay, so Is that. And then look at polychromatic stuff.